To introduce Dr. Youssef Ballout from the Idaho National Lab. Dr. Ballout is the Reactor System Design and Analysis Division Director. He joined INL in December 2018 as the manager of the Fuel Design and Development Department. Before INL, he was the president of Elysium Industry Limited, where he was engaged in leading the design and development.
So fast reactor. We also spent 26 years at the Naval Nuclear Laboratory, NOLS Atomic Power Laboratory, where he worked on nuclear reactor design, reactor materials, reactor thermohydraulics, and reactor structural performance. He had a very long and successful career, so I'll stop it here. Thank you for being with us today, and looking forward to hear about your talk. So let's welcome Dr. Ballout.
I just open by thanking Max for this very nice introduction and for inviting me to come here. I've known Max for a number of years now, and he was visiting INL a couple of weeks back when he issued that invitation. I said, yes, why not? Because coming in to talk to people in our business is very important to spread the words of what are we actually doing at the Idaho National Lab. And what we're doing actually is very important, not just simply for INL itself, but important for the nuclear industry in the country, and in fact the world. Because what we do in this country leads the rest of the world in many different aspects. So let me just open. If this thing, I can't remember. We'll figure it out. So the Idaho National Laboratory is almost exactly 75 years old. And the laboratory actually is the product of how things developed right after World War II. And the Fermi experiment actually that happened actually probably independent of Idaho National Lab and nuclear reactors for whatever reasons, but actually was the segue of what was going on in Idaho after that. So for those of you who do not know what Idaho is, in terms of geography, it is in one of the most isolated parts of the country, pretty much like Los Alamos. Los Alamos is pretty famous, and people know roughly where it is. Idaho National Lab is similar in that regard. Most of the work actually was developed in the desert because it's isolated. In 1949, when the lab actually started as a national testing station, people didn't understand nuclear technology very well. So they wanted to isolate things, put it away from people, keep it safe, and so on. And that's why it was built. Now I talk about safety. Very important for me, as my perspective, there has never been a design that actually made a neutron that is actually unsafe, in my opinion. Smart people work on these designs and we make sure they are safe. We don't really put, oh, that's a stupid design, let's just put it out there in the desert. No, they're all very safe. They're all very, a lot of smart people worked on them with design in mind. I took my kids once into a place where they could put their hand, my two daughters, on the outside compartment of a nuclear reactor, and I did this to them. This is the wall of the reactor. I started doing this. Finally, I put my hand on the design on the reactor, and I pulled it back. And my daughter, who was 14 at the time, said, "Dad, okay, we know it's hot." I said, "What do you mean you know it's hot? I just like you, like the rest of the people who talk about reactors like you. Keep that in mind. Reactors are safe." But then she put her hand on the reactor compartment. She found out, oh, it's cool. Got it, Dad. So that's why I always tell people that you hear a lot. You're in the nuclear business, so I understand that even you can hear stuff that's a lie. We're safe. My daughter can tell you that. She put her hand there. It's safe. One of the most important things that you look at in this, I'm not going to tell you everything in these pictures that you're looking at. One of my favorite is my own business, the S-1W, the submarine in the desert. That actually was initiated, built, put in a big, I'll call it a tub of water, and tested to see what would happen if you put it in the actual ocean. Was that reasonable to really build a submarine in the desert to test it? Yes, it was. It was the first. That has never happened before. We didn't know exactly how this would go. When the head of naval operations heard that this captain, Rick Over, is going to, he wasn't on Naval yet, he was going to put this thing that he's calling a reactor, a nuclear reactor in his submarine. This is not what he said. The head of naval operations said, this crazy guy, he wants to put a nuclear bomb on one of my submarines. That's what people thought at the time. And the rest is history, and we know what that is. So this is the genesis of reactor technology at the Idaho National Lab. Oh, good, it's clear. So Idaho National Lab is actually a very big place. It's roughly 890 square miles. I anticipate there are some international students in here. That's about 2,300 square kilometers instead of 890 square miles. That's a lot of land. It's 3/4 the size of Rhode Island. It is about 1/4 of the size of the country I grew up here. I grew up a lot of. It's about 1/4 the size of that country. So this is a very, very exciting place nuclear reactors. Partly because the fear of nuclear at the time, and you want to stay away from population centers and so on. And so that number there is not 5,700 anymore. It's over 6,000, 6,100 actually, employees at the Idaho National Lab. It's a big lab. And we do many, many different things, and I'll go over them. It's not just nuclear reactors. Reactors are the essence of what's taking place at the Idaho National Laboratory. It's not the only thing. And please ask me questions as I go. You don't have to wait to the end. I'm going to actually just respond on the spot. So the primary capabilities that we have at the Idaho National Laboratory is, well, you see it, reactor, nuclear reactor design and analysis. So it's not that so much that we design these reactors. The public sectors, or the private sector, I should say, can be designing these reactors, and they work with us to help them actually study certain aspects of their design, improve certain aspects of their designs, and actually work with them on proposals to test some aspects of their design. So it's not just reactors we build for ourselves, we don't. And I'll show you which one we work with for ourselves, but the rest of it is really supporting the nuclear industry. And then we also work on integrated energy. Integrated energy is a very important issue because, yes, you have nuclear reactors as the main thing we're working on, but also we have an effort going after solar, wind, hydrogen, and other forms of energy that we connect together. That's the integration part that we make them work together. This is a very important piece of it because there are a lot of people out there who think that solar can solve the problem, wind can solve all the problems, recyclables, whatever you call it, renewable, they can solve all of it. I'm not one of those. I believe it's the integration story that comes together to actually pull the energy to supply all the demands, all the needs, and so on. So we work on that. We work on the rest of the, I'm not going to go over everything, but the one important piece actually is I like to point out human factors. Human factors, really what that is, control rooms. So you have control rooms, and how do you design the control room to make sense out of it? You want to minimize the number of people in the control room. You want to also maximize the ability to see everything at the same time. Less eyes, more people, and or more information at the same time. So we do the human factors a very big deal about how we're moving forward with reactor technology, not just for microreactors, that actually supports current reactors, PWRs that also are in the field today. And then we do a lot of testing, modern simulation and so on, but the testing is very important because it's not that you did the test, okay, you take a piece of specimen, you put it in the advanced test reactor ATR. I'll talk about it more later on. But what are you going to do next? So that you look at the two pictures, look at the two pictures. The top one has the advanced test reactor ATR. The one below it is the transient test reactor. Very unique reactors, both of them. Not only unique because they do things no one else can be done, especially the second one. They now no other place except one experiment. What I know that we can do this. The ATR is exceptional because it's the only operating one. There are a lot of reactors that have been built over the years. Not much is left. They have been shut down, they're dead, they're gone. And it adds to the tragedy of test reactors. It's really a thermal reactor mostly. We can't do a fast test reactor work in it. So we have to do some neutronic absorption magic to actually pull the thermal neutrons out and just run a fast reactor and the capsule that will put it. Not a good thing to do, but we know how to do things if we have to. My point is that not enough test reactors exist in the Western Hemisphere. I don't know what China has on the world. I know Russia has a fast test reactor. France is not operating what they have. And certainly the Japanese, they're not operating what they had. The last one was Joyo, it still hasn't come back. That's a fast test reactor. So those two reactors are very unique. And so those are some of the facilities that we have to the hot fuel examination facility. It is probably the largest one in the world. It is certainly the largest one outside Russia and China. I always say, I don't know what the Russians have, and I don't know what the Chinese, more or less we know the Russians, not the Chinese. So this hot fuel examination facility is really huge. When you take a test from ATR or from CREET and any other reactor actually in the country, and you want to look at it like spent fuel from any trigger reactor. They come here. This is a very unique facility. And then, of course, you have to use microscopes and some special tools. That's the characterization lab we have. And we do a lot of characterization for irradiated materials and, of course, materials that has not been irradiated to learn the effect of irradiation on these materials. And the last one, actually, it's a sketch. Actually, the building now has been finished. It's not operational yet. This is a sample preparation lab that you can bring in it materials that have no alpha radiation in it. So basically, it's low-level materials that can be tested and tested. This building is very special. A lot of people are waiting for this laboratory to be available to do testing. We're all invited. You are invited. Once you have something for it. And then what we have a thing we call test beds, including, I don't know if you can see it in this one, the magnet test bed. I'm going to point this one. Microreactor adjoint under experiment test bed. Don't ask me to say it when I'm not reading it. A lot of people get a lot of high mark from me for coming up with these beautiful names. But I remember the magnet. But magnet is basically, it represents a small microreactor. And you can put the materials of a microreactor in it, or some aspect of it, like the heat pipes. The nuclear heat pipes were tested in this. The last one was a single heat pipe that was intended to deliver data for US in-house reactor. I'm trying to remember the name of it, that they would use heat pipes and then we tested just one. There'll be a bundle to be tested later on. And what you see in the right, you see cars and you see other things. So that's like the integrated energy business we're in. Dictates that you need to also test batteries from cars, from vehicles, or other applications. In the back of this building, there's a whole facility to look at bioenergy. They can also municipal waste or municipal trash also convert it. We do a lot of these things. It's not just a nuclear laboratory. So it's the Idaho National Laboratory, not the Idaho Nuclear. We do a lot. So this video is not going to work here. So let me just, I'm going to tell you what the video is. The video actually that didn't work, it's about a minute and a half, taking you through the history of nuclear reactor technology since the end of World War II. The point of it, you would have seen reactors that were built in the United States, and then things migrated to Europe, like France, England, and then not even those countries with the new reactors anymore. Things going to India, going to China. Russia was there right from the beginning, and so on. Ended up, me basically telling you what happened. Where are we as a country? Why are we not in the effort of building this reactor? So you can just look at this. At the top is China. 23 reactors under construction as of last week. Look at us at the bottom. Just one. We're building one today. What does that tell you? We're afraid of nuclear. We hate nuclear. What happened to us? Well, many things happened, but one of them is the assumption that you got to the top of the world in nuclear technology and you're going to stay there. Everybody's gone. Everybody. The world has changed and everybody wants to have a piece of the nuclear pie. Hopefully only the peaceful part of it, which is nuclear energy. So all these people, they're aware of what Admiral Rickover said. So one of the things that he said, I'll just summarize, I'm not going to read this, you probably read it. Anyone can build a nuclear reactor. And nuclear reactor technology itself is very hard. And ask me, because I have been involved for many years, decades now, 3 decades involved in one way or another in the construction of a nuclear reactor with a very well understood design. We know the design, yet building it is very serious business. It's not simple. It's not like building a Tesla or a Toyota. Nuclear reactors are much more complicated for many reasons. So the father of the nuclear navy warned us about this. When you have an actual design, you're going to build it, you're going to find out that, and we're going through that right now with one of the reactors we're building. It is more expensive than you thought. Not everybody has the materials you thought they had. The supply chain that you think is there is really not there. They're waiting for you to ask for it before they can actually supply. And the cost grows with time. All of these things are real. And that's what makes real nuclear reactors. Does it have to be like this? No. But this is the experience that Admiral Rickover told us about. Beta reactors are easy. Real reactors are hard. That's why I said nuclear power is not impossible. We've been doing it for a long time. But it's never easy. And that's where real good engineers come in, people like you, to actually make it more possible. So first, what are microreactors? Never mind the definition. Definition to me is not real. What do I mean by it's not real? Initially, he said, well, if it's 20 megawatt electric or less, it's a microreactor. That actually is not really the definition anymore. It's more or less the idea that you can build it somewhere and then assemble it on site, not build it on site. That's one of the aspects of it. Batteries that you can actually put on a reactor and deliver them to actually put them on, plug and play, and get them going. But these are the aspects of actually what makes a microreactor. So it's not one thing, it's a collection of things. Cost is not really one of them. The economics itself is not part of the definition. You could make it part of the definition if that's what you want. But ultimately what it is mobile. I can build it in Idaho and deliver it to New York on a truck or on an airplane or some other means on a train, any form of communication or transportation, I should say, to deliver this new reactor to where I need it. More importantly, some reactors are actually designed to also be retrieved. So you run it for a month or a week. If it's a disaster, say for example, Puerto Rico island was hit by a hurricane, I believe in 2019, and everything on the island was lost. All form of electrical energy were gone. How do you run the hospital? That's one of the very first things we always think about. Oh, the hospital doesn't have electricity. The hurricane destroyed the generators, which actually happened. How do you run this thing? A fission battery, for example, which is a form of microreactor, not exactly a microreactor, can be delivered on a ship. You bring it onto the island. You actually connect it to the grid that exists, or repair the grid if it's a big disaster, and run the energy for the hospital. So nuclear reactors are unique in that capability. And then they can run for a long time. Once it's done, for the reason that you needed that emergency to be responded to as the removed, you take your reactor back to the facility where it started from, or you take it to the next place where you need it. That's what a fission package is, plug and play. And so those are the aspects. So you're talking about your lifetime, 5, 20 years, maybe. Refueling every 2 to 10 years, maybe. Again, it's all definition. The definition is a little bit soft. So the point is to deliver the message. Microreactors, a lot of people are working on them, and we will be looking at some examples. I already went through a lot of this. The possible markets, places. I would say you start from disaster relief. So this is really not at the bottom, should be at the top. But again, this is in no particular order. I like the marine propulsion thing because of the following. Propulsion on the sea and in the sea, under the water, has been the domain of the military technology. That's what we use it. But there's no reason that these behemoth big ships that actually transport thousands of containers and cost a lot of energy for their movement, why we can't use nuclear reactors to actually power this. It's in the works right now. In the past, there used to be a lot of pushback on this type of technology on the civilian marine application because of the potential of the military usage of such a thing. There is a little bit of a change in that technology. So we'll see how that goes. Again, I basically went through most of these things. One of the areas also advanced reactors, advanced reactors in general, but these microreactors that bring on board is the idea of very small exclusion zones. You don't have to take 20 miles or 50 miles and then just no bird can fly over this area almost and make it impossible for all of these things. Those reactors are designed differently. The safety aspect is different. And the hope is we end up with reactors, and of course, federal regulators will have to play into that, is to minimize almost to the nuclear island where you actually can protect the reactors.
That would have to be because seaports are almost always in very densely populated areas.
That's an excellent point. It's actually, when U.S. submarines, for example, travel to very few ports they go to, but very few ports actually have also the capability to receive them. So certain things are done to allow them in. But once they're in, you actually, if you didn't know there's a submarine here or a nuclear reactor sitting right outside, you would not know. I've been to submarine bases and you would not. It's safe, it's quiet, make the noise. Any other questions about this? Please stop me, ask a question, make comments.
So I'm wondering if you have one of these for disaster relief and there's some technical issue and has to shut down, can they start up again relatively soon, or do you have to wait for the xenon to decay?
So these reactors are hopefully all designed in a way that you can shut them down and you started them, you would be able to start them soon, which means it's not like a civilian reactor, you have to wait for it to come back, none of that. Again, those are design features that in the mind of the designer. Not everybody will come to this way, but that's like when I say fission battery is plug and play, it's really plug and play. Now let me mention one more thing. Let me just put the second page. Okay. So before I go to this, I'm going to say more about the fission battery. Fission battery is really a small thing. We're not going to be building a fission battery. We're building other reactors right now in the lab, and you'll see them. A fission battery, instead of us building a fission battery, we are actually assessing what R&D gaps exist and then go after them. So if, for example, we decided we don't know enough about the transportability of a reactor, the fission battery, that is limited because it's too heavy. Nuclear reactors, they tend to be very heavy. And a lot of people say, I'm going to just take this reactor, put it in the back of the truck, and take it somewhere. Which truck? And you're going to put it in a KC-55 or an airplane, and just which airplane? Those things are very heavy. So one area of research, for example, is to look at some of the heaviest materials you could see in a nuclear reactor. Shielding is very heavy. And structural materials on the outside of the reactor, they tend to be very heavy. We're working on it through R&D. So we're not going to build it, but we're going to enable the private sector to look at the R&D that we're doing and let them pick from that to actually look at potentially what can be in their design. So somebody was sitting in my office a couple of years back, and we were talking about this. I said, I like Swiss cheese. Why don't you make materials like Swiss cheese? And he said, what are you talking about? You make it like that. And you may be able, in the holes of Swiss cheese, put something else that also can absorb radiation and neutrons and so on. So they're working on that. So sometimes it sounds like you're dreaming, but that's what engineering is all about. It is the imagination, not what's on the table, it's what's in your head to put on the table. And so we are creating R&D space for people to enable that technology to exist. So I picked one thing to talk about. Many others. You know, actually, also for the fission battery, issue of cost is a big deal. How do you minimize cost? And also, so what R&D do you do on cost? Well, cost is not just simply the cost of the reactor, the cost of where it goes. That's part of the R&D that you have to do, the location of the reactor. Ultimately, it will be a simple reactor that can be plugged into an NE and then take away when you're done with it. And like you asked, can you really turn it back on soon? Yes. It doesn't have to be weeks or months. This is just to give you a feel of the microreactor companies. This isn't by any means exclusive. Yes?
So it's representative with the application list you have in the previous slide, is that
Mostly not totally. It's not intended to do that because, and I'll tell you why. Westinghouse is a big, they do ignition, that's the name of the group. But they also do many others. So this represents some aspect of what you saw on the other slide. Right.
so how was that generated of possible?
On this,
No, the one of possible mark.
again, sometimes talking to the private sector what they want, what they're looking for, and sometimes talking to the R&D guys that we have. What do you think we need? And also, sometimes also we talk to DOE and they tell us, well, we're here because they talk to somebody, told them this is what we're looking for. So it's a collective of many different ideas. And also, it's not exclusive. Nothing you see here is religious. We may look at the list and we say, the most important one, I said, initially, the primary definition of a microreactor is 20 kilowatt megawatt electric or less. That's not there. It really isn't there. But we have it as a general guide for people. But it can be more if it fits in the other attributes of what a microreactor.
So that's what Idaho has defined as priorities of target
More or
market.
less, yeah. More or less. Yeah, but again, it's not solid. Again, you look here, you see, a lot of reactors. It's much. At least there are two reactor companies I'm aware of. One is started, the other one is not yet. I'll call them the Cube companies. New Cube, and I forgot what the other Cube is. So advanced reactor companies and startups are actually happening pretty often. And some of them actually fail out the business too. Some showed up and disappeared. So you saw the names of these companies and others who are not on this list. So how do we enable it? What does the Idaho National Laboratory do to actually make it possible for these companies to move from the idea stage to the next stage, which is whatever they define to be the next idea, if it's design or testing, whatever it is. So we have two centers, GAIN and NRIC. GAIN is Gateway for Accelerated Innovation in Nuclear. This was created in 2017 by the US government, US Congress. What it does basically, the easiest way to do it is Westinghouse's design and invention. And they want to test in a nuclear reactor their heat pump they need for the design, or they need to test their fuel in a nuclear reactor. They don't have these facilities. They should not go after getting these facilities. It's horrendously expensive to go build a test reactor. They're not going to do this. We have a test reactor for that. So they come to us and they apply for what's called a GAIN voucher. I think the guy who created the GAIN voucher, his father worked for a movie theater. That's why he came up with the word voucher. I would not have called it voucher. But anyway, they get a voucher if their proposal is convincing to INF. We actually, we look at it, we evaluate it, and we say, yeah, that makes sense, let's bring this test here. The value of the test is about $920,000. That's, and then the company that came in, the startup or the private sector company, they also have 20% share. So it's, they have something to pay in it, so because they have skin in the game. The real cost is a lot more than that. So when I say that I'm going to take your piece of equipment and drop it in my test reactor, I run it there for 6-7 months or 1 week or 1 day, doesn't matter. It's very expensive to put all of these people to do all the work, all the analysis. Because before you put anything in our reactor, we do the analysis. You do the analysis to what you want. We repeat that to make sure that what you say actually is safe inside the reactor. I don't want to destroy the reactor, so we do the whole analysis again. And so the cost of doing all that work is really not shown in the cost that we report to you out, like $920,000. And many other types of tests. If, for example, you have a new piece of fuel that you want to actually do a flash test on, that's where the treat reactor comes in. So in transit test reactor, it goes up into very, very high temperature for a fraction of a second, maybe a second that you expose the specimen to it and then bring it back down. So it's a transient test. What happens? For how many test reactors in the Western Hemisphere that are like this exist today? None. So very, very expensive technology, and it takes a lot of preparation to actually do that test. So what you're getting out of this is a lot more than the dollar value that you're looking at. Now, what is NRIC? NRIC is even more important for the foreign research. Is the National Reactor Innovation Center. So what NRIC is, a startup company, they start talking to the Idaho National Laboratory, talking, for example, about locating a test reactor or prototype, or even an actual reactor that will sell electricity if the case is correct. We're going to build it and operate it at the Idaho National. And that's a very, very serious business. You know, build a nuclear reactor on one of our facility. Well, the cost is in the tens of millions of dollars, and actually could be hundreds of millions of dollars to do so. So Henry is working with what we call demonstration reactors that actually have to be built at the site. And then we also have risk reduction reactors. So risk reduction, that means that the two reactors actually are upfront to be built first. If for some reason we don't finish one, or we found a flaw in one of them, we can pick one from the risk reduction designs that can actually be brought. It is belt and suspenders, so make sure that we actually deliver on these things. So any questions next?
So are all your microreactor concepts for electricity production only? Or are you thinking about steam or hydrogen production as well?
First, we don't have any of the reactor designs or some, except for one model. Those are the private sector's ideas, and some of them actually talk about the reactors to generate hydrogen, to actually help in the generation of hydrogen, and some generation of heat and heat storage. So it's a mix. It's not just making the electrons.
You work with any foreign companies, not exclusively
No, this is only for American companies. You could be a blue company, some of them could be US and Canadian. Now we can work with that. But it has to be a US-based company.
Is the US based requirement in order for gain to found it or in order for them to be a customer?
Because the American taxpayers are paying the bill. That's really why. It's not a technology issue. It is who's paying the bill, the American foreign, American taxpayers, so we can't be supporting a foreign company. That's really the base for it. It's not a technology issue whatsoever.
It's Enric specific, it's not gain specific.
Well, it's, so if you may see someone testing with gain, the rest of the example, because they also Canadian, right? But they are also US. So it could be a dual company, yes, you can have this. So some of them actually have foreign subsidiaries, and that's okay. So I talked about Enric and what it does, and the two primary facilities right now that Enric is building. See this dome? If you ever visit, some of you have, the Idaho National Laboratory and start driving into the desert, we have the materials and fuel complex. And one of the things you'll notice is this dome. This used to house the EBR2. What I didn't tell you originally is that the Idaho National Laboratory built also EBR1. And that was actually turned on by some interesting, funky way by President Eisenhower from the Oval Office. I'm sure there was no cable at that point in time, probably a phone license, turn it on. But at least the president in the White House pushed the button and the reactor went quick. And so that's EBR2, the second to EBR1. But I also didn't say, I was waiting to this point, is that the Idaho National Laboratory actually over the years rebuilt 52 reactors. 52 reactors. And so we have a lot of experience in building reactors. I only know one person is still alive working in the lab that was involved in those reactors. Because the last one was 74. So even if he was a kid at the time, he's old now. And so those facilities will house, so that zipper there, so this is a zero power reactor, this will call a zipper. No, foreigner, what is it, extraterrestrial did not land on that building. We always ask about is this a spaceship? It's not a spaceship. What is it, Roswell was not involved in this. And so this will house the Terra Power reactor known as MCRA. You'll see it in a few minutes. multi-fluoride reactor experiment. That's the name of that reactor. And this one here, we haven't finalized who's gonna go in. But we'll just wait for a customer. There's also Pele, so you're gonna be seeing me talking about Marvel, Pele, and McCree. Those are actual reactors we're building. This one will house a reactor that is not named yet. And a lot of people are actually interested in that. So we have the facility for it. And the other one will house the McCree reactor. And I'll show you in a second. Let's see if I can. So before I get to the details of the three reactors, look, this is the timeline relative to when we think a reactor will go critical. Those days are not invented by us. Those days are given to us by the private sector. So if, for example, Taylor says Hermes will be built in 27, we said it will be built, not built, but also go live in 27. Because that's their decision, that's their timeline, and we just work with it. But I would have to say it this way: everything you see here is notional. So what did Admiral Rickover say? He said, Victor, is hard. And you may hit a snag here and a snag there on the way. And so this can turn to the right. I've never seen anything turn right, and they can turn right. And when it turns right, that'll be interesting, but we haven't seen it that way. But here, by the end of 2025 calendar year, we expect that Dome will be ready, Project Family will be ready. I'll tell you the details of these two, and then Marvel will be ready. So remember that we call 53 and 54 and 55 and 3. Why? Because I told you that those reactors that we built in the past, the last one in 74, was number 52. And therefore, Marvel is 53, and then Pele is 50. Now you can just say, how do you know? Well, we have a very friendly competition between the manager of Pele and the manager of Marvel, and they're going like this: I'm first, I'm first. So everybody wants to be 53 actually. So the reason we picked 53 first because we proposed 53 to DOE. So you can just see there's also, go ahead.
What's the budget difference between Pele and Marvel?
You have to ask that question. Money. You don't know. Actually, I'll tell you why. Pele is actually the Department of Defense reactor. You ever work with the Department of Defense? Toilets cost $65,000. Used to be, remember, if you're familiar with, used to be the cost of toilets in their outboard. Look at that. Pele is a military reactor. It will cost a lot more than Marvel. Marvel right now is about $150 million. So pretty cheap compared to anything else you know about nuclear reactor. Pretty cheap. No, this is DOE supported. Yeah, so therefore. So when you say INL budget, the answer is a tricky thing. We get funded to actually do this work. We're directly funded to do the green Marvel. So it's directly supported. And Pele is directly supported by the company. And, because of the nature of that design, what it will do, it's a very different design. So you'll see later, I'll talk about part of the reasons kernels of TRISO are used in Pele because it's a very robust. And kernels, they can be one of the easiest, not the easiest thing, but one of the things that you probably could do what you need to do after an explosion or a kinetic event, go pick them up, send a robot quickly, build these out. Cannot do that with anything else. That's why Pele uses actually price. Any other questions? One thing you don't see here anymore, we used to have 2029 the new scale reactor. What's that?
I was doing a design project for Dr. Pearson's class that involved using a nuclear reactor. And in the middle of that project, we heard about the whole,
Right.
the whole.
It was shut down, I believe, in November. It's not the design. It's not anything that involves the lab itself. Because NuScale decided to build this reactor and deliver it based on number of subscribers from the municipalities, right? That's really what's called UAMS, Utah Association of Municipal. It's just something like that. So basically, it's towns and cities that come together and buy electricity from NuScale, from that reactor. If they reach, they said, if they don't reach 80% subscription, they cannot move forward. They cannot. So that's fine.
So you said that Pele is funded by the DoD, are using TRISO because it's easier to clean up?
No, that's one of them. I'm just giving that as an example.
Okay, but, so they're not using TRISO because they're anticipating that there will be some sort of explosion behind the DoD stuff?
No.
Okay.
Listen, so you'll see in a minute. I'm gonna talk more.
Is the business relationship between INL and the DOE and the DOE as an architect, engineer, constructor? For the
There's an organic relationship between Pele. Marvel is totally anti. So Pele and McLean are owned by somebody else. Pele is really Department of Defense, and it's not exactly the Department of Defense with the big details. Yes, government is pretty big. It's under the so-called Strategic Capability Office, which actually is part of the country. They work with us on every aspect before they're going to locate the reactors and what we can do with the reactor. So I can't tell you everything about this. Actually, some aspects, many aspects of this classified. The other two are not. They may not be classified, but some aspects of this is right. So we work with them on siting. We work with them on helping them talk to the NRC. Like one of the guys that works for me, Griffith, and licensing issues. So we bring our expertise to all of them. So once it's deeper than someone will do the analysis. So I'm not going to repeat this. Three major reactors working on Ballout, Marvel, and MCRA multi-chloride reactor experiment. All three are microreactors. So that's one very important feature of these reactors. So we'll go to Marvel. So why do we need Marvel? It's a very tiny reactor. I personally would not want to buy Marvel. Not for me, not for the little town I used to live in upstate New York, Clifton Park. Wonderful reactor. Why wouldn't I want it? It's small. It will deliver about 85 kilowatt thermal, and actually it was designed for 100, but then we backed off a little bit because of the features of just to protect these guys, the Stirling engines, because they have a limit that is 100 kilowatts. They say, it's not going to get the limit. It's just looking off. That's why. And so, more importantly, it's 20 kilowatt electric, which makes it probably half of this building, maybe less, can be powered by something. It's pretty tiny. It's not very big. So why are we doing it? Why are we buying it? One, everybody talks about a microreactor. No one's building it. That's one thing. So we're going to show the world. Yeah, you can build a microreactor. Two, we have not been building microreactor or any reactor, in fact, at the Idaho National Laboratory. We need to reestablish our skill in that. It's paper still right now. We need to come back into the business fraction, building the right reactor, and then relearn how to not just operate, how to restart or start, I should say, a brand new reactor. We're going to be looking at these things and doing it. And also, the microreactor industry, they really want somebody to build one of these things to make sure that everything we say is real. Although, my microreactor may look different from your microreactor, but at least I started the process. So that's what the Idaho National Laboratory is doing. And also, all aspects of this reactor, we don't are going to be in the public domain. So we're gonna just tell you everything in it. How much time do you have, Max?
It's out of time. It's 4.
Well, let me just tell you the key issues that I brought in. Marvel, we are building. It's actually, you see all of this thing, I wish I got my own picture in front of this. We built it. It was shipped to. See this thing here? That was built actually at the Idaho National Laboratory, at the MFC, the Materials and Fuels Company. It was built there, it was shipped to Pennsylvania. This is, other people call this an integrated test. So you put everything in it except one thing, no fuel. It will be heated by electrical resistance, and you run all aspects of it. So far, everything we want, especially natural circulation, it works. Now, my response to natural circulation as a little boy, I used to sit next to a water boiler to take my shower. It was natural circulation because you hit the water from the bottom and you hit the magic of the hot water comes from the top. When you put your hand at the bottom, you find that water colder at the bottom than it is on the top. I asked my father that question. It doesn't make sense. As a little kid, he told me about natural circulation. Because he was at the airlines, he had an idea. He explained it to me. And I always say, why would anybody not believe it will work? But we have to test it. So this is just I'm gonna skip it. Basically, it's just telling you, we have this under testing in Pennsylvania. Now back to your question. You asked about the difference between failing and the other reactor and so on, and why are we worried about explosions and so on. Because this reactor actually will be deployed into war zones if necessary. For a reason. 80%, let me repeat the number, 80%, 80, of US casualties in Iraq and Afghanistan were not in the battlefield. We're actually transporting energy, diesel and the lights, from one place to the back of it, or where we have a base. That's what most of our casualties. Having a nuclear reactor on the base will alleviate all the problems. If you have a battery missile somewhere that you need to connect it to, or just the base, get electricity to the base, you don't check these. The reactor will do that. And once you're done with it, you close down the base and you're in that foreign country, you put it back on the top. That's the point of that reactor. And also we have bases in Alaska today that actually would benefit from having a reactor like this in that little town, because the shipment of energy to make electricity or other forms of energy, heat and so on, can be done. So that's what the point is. So is this new? It's not. We can look at these things from the 1950s and 60s, where actually the Army already worked on microreactors. They just didn't call them microreactors. It was just called reactors. This is very, very old stuff. But all these, but nuclear reactors don't get old. As long as you get them right. One of the most important things in nuclear reactors to me is not the fuel. It's the materials. That's actually what makes the reactor reliable. It's the materials, structural materials. Again, portable because what I said, they with human American lives, soldiers, transport the other forms of energy so frequently. So this will stay American. And then MCRC, multi-chloride reactor experiment. It's not new. What do I mean by it's not new? the country built already a molten salt reactor in the 1960s. We operated that at the Oak Ridge National Laboratory. Successful. We learned a lot from it, especially material stuff. And then we're repeating that experience now using chloride. This is what a consortium in Southern Company Power and others, of course, working right now, building the degree itself. The key in the name of the is the last method. It's an experiment. It's not going to make electricity. It's not. It's going to make heat. Basically, it's an experiment to see how the reactor will operate. We'll run it for 6 months and we'll be shut down. And then tons of testing will be done on what happened in those 6 months. I guarantee you, that's why I think those tools will go more than 6 months. Once we start testing it, we probably want to see more. And we'll go into Lotus is actually, it's a fancy name for that zipper building. I told you the space ship that landed on top of that building, or bigger. That's where MCRE will go. You didn't ask me, but those reactors, the ultimate reactor will be HALO, which is high SNO enriched uranium. Basically, it's fuel just below 20%, and somewhere closer to 15% for some of it. The building that will house this reactor, the reason it is zipper is because zipper actually is going to be run with high enriched uranium. So it's 93% from it. For practical reasons, we have the fuel, let's just run it, because we don't have enough fuel, so let's just do it. So one thing actually is very important to note, to mention here, is the last thing I'm going to go over, is the fact that we made the fuel, which is a very important accomplishment. And those are tools that actually used to make the fuel. I'm going to show pictures of. Yeah. And then we started with, look at the first number, 10 grams of uranium were used to make a very tiny small batch of uranium chloride. And then we graduated all the way to 9 kilograms. This is the limit that we can go to because of the highly enriched fuel. We can't put too much in a spot. When you go down to just about below 20%, the batch will be much bigger. And ultimately, this is what you're going through. This is depleted uranium metal. Actually, it is melted into that pod. It's just literally the hammer. We just knock it out, take it out of this thing, and they break it apart to get this. You heat it up in a resistive system, and then you get the molten fuel. That's really what it is. Most importantly, is on the time. And then in addition to doing it, we tested it also. One of the 4 reactors at the Idaho National Laboratory. We are the 4 reactors. ATR, the advanced test reactor, the ATRC, is that actually is a very, it's a duplicate but very small power reactor of the ATR. And then this is NRAD, which is a very fancy neutron radiation reactor based on an old university. I forgot which university came from, reactor, trigger type reactor. And then the one I showed you pictures of earlier, the treat reactor. So we took a sample from that fuel, we tested it here just to see how it would perform. And this is not a bad time. This is actually a piece of unmelted fuel. It was molten and put into the test sample, and then it went into the NRAD reactor at the ATR facility. Actually, that's what it is. I'm sorry, at the hot cell facility, because the reactor is in the hot cell facility. It was tested there, and more work will be done. Finally, what I want to tell you, because I have students here and professors, but sorry, more important students here. I would like to see you apply for internships at the Idaho National Laboratory. We have internships, and please consider doing that. Tell me if there is a specific topic on your mind. Write me. Max has my information. You want to be connected to one of our engineers. So PIs, the principal investigators, because you have some work on your mind, we can do it. And of course, once you're done and you want to look for a job, Iris is a great place to work. I know it's good. Thank you very much.
Okay.
We have time for further questions, but I'm sure students will stay on and ask questions about internship. Thank you.